Welcome to this demonstration on symmetric encryption using OpenSSL, where we will see how two virtual machines can securely exchange encrypted messages. In this video, our main goal is to encrypt and decrypt files using the advanced encryption standard using 256-bit keys. Advanced encryption standard 256, which is one of the most widely used encryption algorithms. This demonstration will simulate a real-world scenario where two systems, we have the sender Alice and the recipient Bob, where they need to securely exchange confidential data over a network. To achieve this, I'm using virtual machines, so I did set up two Linux virtual machines. The first one is the sender VM, representing Alice, and here where we will encrypt the message using the AES-256 and securely send it to Bob. The recipient VM, which represents Bob, will receive and decrypt the message using the same encryption key. This setup mirrors how secure communication protocols work in real-world applications such as secure file transfer, encrypted messaging, and virtual private networks. By the end of this demonstration, you will understand how symmetric encryption works in practice, how OpenSSL helps in implementing strong encryption, and why key management is critical in secure communications. Now let's move on to the practical setup and start implementing symmetric encryption between our two virtual machines, Alice and Bob. Now let's start with the first step, generate the symmetric AES key. I'll be using the sender VM, Alice's VM. Now that we have both the virtual machines are set up with OpenSSL, let's begin first by generating the symmetric encryption key. Symmetric encryption relies on the same key for both encryption and decryption. So we need to create a secure 256-bit advanced encryption standard key on the sender VM, Alice. To do this, we are using OpenSSL rand command, which will generate a random value. To start with, I'll write the command first, OpenSSL rand, and then I'll choose the base 6432, and then I will save this into a file called secret.key. So the option -base 6432 ensures that we are creating a 32-byte random key, which is 256 bits, the required key size for AES-256 encryption. We are saving this key in a file called secret.key for later use. Now I need to verify the key file exists. So I'll simply use the list command to verify that the key I have created is there. So when I do ls-l, so what this command will do will check if the file was created successfully and will list the file along with its size and other details. The key will remain private and must be securely transferred to the recipient. Remember, we are using symmetric encryption, so this key must be kept secret only between Alice and Bob. As you can see, the key is created, so I can see the file with the size, with the date it was created. Now I need to do one thing, I want to view the key. In reality, we don't view the key. This needs to be secret between Alice and Bob, because this is the key that will be used to lock and unlock the message. So what I need to do now, I'll use the cat command. So I'll do cat and then the secret key just to do what? To view the key so we can see how it looks like. So when I do cat secret key, here we go. This is the key showing there on the screen. So this was step one, where we did create the secret key. And this is what I need to do or to use as Alice and as Bob for decryption and encryption. So now in step one, we have created the secret key that Alice and Bob will use for encryption and decryption. Now in step two, what the sender Alice will do will encrypt the message using AES-256. So first, Alice will do what? Will create plain text file called message.txt. To do that, I'll use the echo command, and then I'll write some confidential data for the recipient into a file called message.txt. So this is what the sender will do in this scenario, assuming this is the confidential message to be sent to the recipient, Bob. So that's what will be done first, and then what we'll do, we'll verify the file exists. So now I will verify that the file exists using the ls command -l, and then I will look for message.txt. So I want to look for, no, actually it's txt. So that's the message I have just created, which has the text confidential data for recipient. Then what I will do, I will encrypt this message using advanced encryption standard 256. And as you know, we are using OpenSSL for that. So I'll be using this command, Let's chat about this command and see what it does. So first, I'm telling OpenSSL, can you please encrypt the message in the file message.txt. What I'm using, the algorithm AES 256, and I'm using the CBC mode. To add some randomness to avoid or prevent rainbow table attacks, I'm adding a random salt using the dash salt. And then we are using the password-based key derivation function, which will make it a brute force resistance, or will make brute force attacks much harder. And then, like I said, in message.txt, so this is what we want to encrypt. And the output, the ciphertext, will be saved in message.enc for encryption. So that's the name of the file, or this is the output encrypted file. And then I need to pass for it the secret key. This is what we have created in the previous step. So that's secret.key. I'm passing this to the algorithm. And this command should encrypt the message.txt and save it into message.enc. If I hit enter, then this should have worked. How can we verify? Simply like we did before. But before that, I'll just clear the screen so I can start on top. And now I will do ls and then dash l for details. And this time I'm doing the message.enc. That's the encrypted message. Let's see if it's there. And I can see the message.enc is created. Now I want to view the encrypted file and see if I can see some unreadable characters, which is what the encryption does. And this what means to us that the message is now securely encrypted. Let's use the cat just to view the content of the message.enc. And here we can see the salted ciphertext by using AES 256. Now in step 3, we need to send the encrypted file and the secret key to the recipient Bob. To do this, we use Secure Copy Protocol, SCP. This will allow us to transfer files securely between two machines. So I'll be using the SCP protocol, and I'll be sending the message.enc. This is the encrypted message. And then I'll specify, this is the syntax of the SCP command. It's the user on Bob's side, add the IP address of the destination, and then followed by the path where you want the file to be saved. Kelly here in this scenario is the user at Bob's machine. Since symmetric encryption requires the same key for decryption, we must also make sure that we securely transfer the secret key. Let's first send the encrypted message, and this will ask for the password on the other machine. And now I got 100%. That means the file has been transmitted. Then I need to share the secret key. In real world scenario, this should be done using a secret key exchange mechanism like RSA encryption or key management system like Diffie-Hellman. But what I will do now in this case, I'll just demonstrate the SCP when I send the key. So I'll send the secret.key, and then I'll do Kelly, this is the user at Bob's device, add the IP address, which is in this case 192.168.162.131, and then columns, I specify the location. I'll make it the same location where I did share the message, and Kelly here is the user directory at Bob's VM. Then if I hit enter, it will ask for the password and then 100%. So now I'll go at the recipient VM and check if the files received. So if I go to Bob's VM and do ls, this should show me the two files there, the message, the encrypted message, and the secret.key. Now the final step in symmetric encryption, Bob received the message and the secret key. So Bob will now decrypt the file or the received message. We'll use OpenSSL, so let's decrypt the message using OpenSSL. So the command here is similar to the encryption, but we add an extra -d option, and this is for decryption. So let's do this together. So I'll do OpenSSL, and then I will add the -d as you see, this for decryption with the same attributes, the same algorithm, the AES 256 CBC that was used for encryption. The same algorithm will be used for decryption, and the same salt and the same extra options we added when we encrypted the message we'll use when we decrypt the message. The only thing we added to the command is the -d, indicating that we want to do decryption to the file. And for sure, we did give it this time the message.enc, the encrypted message. And we want to output this into a new file called decrypted.txt. And we are passing the secret key to this command, so we can use the same shared key to decrypt, which was used initially to encrypt the message. and that should create a new file called decrypted.txt, and we need to verify. So the original message has been successfully restored. This can be verified by using the cat command to check if the decrypted.txt has the message. And here we go, confidential data for recipient. So we are able to decrypt the message, confirming that our symmetric encryption and decryption process work perfectly. While symmetric encryption is effective, it has a major limitation, as we discussed in previous videos, the key distribution. If an attacker intercepts the key during the transfer, they can decrypt all messages. To improve security, we use hybrid encryption, where the advanced encryption standard key is encrypted using asymmetric encryption like RSA. The encrypted key is securely transmitted in this case, and the recipient decrypts the key and uses it for symmetric decryption. This is exactly how TLS, HTTPS, VPNs, and secure messaging apps protect communications. That completes our demo on symmetric encryption with OpenSSL between the two virtual machines, Alice and Bob. We successfully generating an advanced encryption standard 256 key, encrypted and decrypted a secure message, transformed the encrypted data between the machines, and discussed key management and security best practices. Subscribe for more tutorials and try this in your setup and share your results in the comments. Thanks for watching and see you in the next video.